Hello, everyone. I'm Hao from Preda team. I'm excited to introduce Crystality to you guys. And Crystality, actually, the two words, we make these one words, crystal plus solidity. That means we want to provide the structured solidity. Let's start. Oh, this work was published in ACM PPoPP conference this year, a premier academic conference for programming language. My presentation includes three parts. The first one is a Crystality design. It is a novel program model for smart contracts on parallel EVMs, enabling transactions to be executed in parallel under explicit developer control. The second part is Crystality AMM. It is the first parallel AMM prototype. This prototype can process AMM swap transactions concurrently, even for a single trading pair. And in our preliminary results, we found our methods can achieve up to more than 10 times speed up over the sequential execution method. The third part is GPT-based auto transpilers. This transpiler can help developers to migrate Solidity contract to Crystality, simplifying the adoption. You may notice many blockchain systems do not provide the parallel execution layer, and the newer systems provide the execution layer in different ways, like Sui, Sei, Monart, Aptos, and many others. Mostly, they use two different methods. The first one is an optimistic one, and the second one is a pessimistic one. The optimistic methods, the system assumes there's no conflicts in transactions and allow the parallel execution. And when they found there is a conflict during the validation, they roll back and re-execute the transactions. In the pessimistic methods, the systems pre-check all of the transactions and only allow the transactions without any conflicts to be executed in parallel. We also check the new EIP, the EIP 7928. They propose a block level access list. Intentionally, it is for the parallel I/O, but I think this can be combined with the parallel execution. The key challenge in parallel execution is resolving state conflicts. Different with the previous parallel methods, we propose a Crystality use a different way. We break down state access and dependencies for each transaction and execute transactions state by state, eliminating all of the conflicts. We think the EIP 7928 and Crystality is a perfect match. Let's check how Crystality executes transactions. We assume we execute n-token transfer transactions on P parallel EVMs. Each transaction has a unique source account SI, but shares the same destination SX. In Crystality, we also assume one EVM, in this case, EVM P3, exclusively updates state SX, and the EVMs P0 to P2 handle other states. At time 0, P0 to P2 node 3 transactions, TX0 to tier 2, to execute and generate 3 relays. At T1, P0 to P2 node 3 more transactions, TX3 to TX5. At the same time, P3 execute 2 relays. At T2, this pattern continues and going on. In this way, Crystality achieves an intro-transaction level parallelism in a pipelined manner. This table summarizes key takeaways of Crystality. You can find in this table, Crystality is distinct with previous method, especially in parallel granularity and execution model. Let's check the detail how we implemented Crystality. We think the major problem for the parallelization is a smart contract language like Solidity, Move, and others. They all use a shared everything architecture. That means all transactions can access all states at runtime. Additionally, this programming language uses sequential program model. It is very difficult for developer to express parallelism in depth and algorithms. We use 3 different major steps, to implement Crystality. The first step, we partition states into non-overlapping segments. Each segment assigned to a dedicated EVM instance at runtime. For the second step, for transactions in this example include 2 states, Si and Sj. This transaction is first processed by EVM instance managing Si, and then processed by another EVM instance responsible for Sj. The address to EVM mapping is computed using this formula. We use the lowest n bits of an address as the EVM ID. The execution flow switching between EVMs is managed by a relay directive. It is explicitly defined by the programmer in the program. We introduce Crystality directives into Solidity. Our directives includes 2 major parts. The first one is programmable contract scope. These scopes guide the underlying system for data partitioning and storage. The second part is asynchronous function relay. This keyword is used to manage execution flow across different virtual machines. I show the example of Solidity code and Crystality code in this picture. On the left-hand side, you can find this is ERC20 Solidity code, and on the right side is Crystality code. It is really simple to add the directives. We use addAddress directive to define the binary variable that guides the underlying system to partition data by address. And then we do the similar things to add the addAddress for the to define transfer function. It enables this function to process different incoming transactions with different EVM instance. When we meet the state switching, in this case, from the signer address to the page address, we use a relay to define this switch in this lambda expression. This is our preliminary results in Crystality. We compare Crystality to Solidity on EVM, Sui and Aptos on their own execution engine. We can find Crystality has much better performance. We develop Crystality AMM. Our key motivation is to parallelize swap transactions even within a single pool. Our key insight is that price change is primarily driven by large transactions. Using historical data from Uniswap pools, we found more than 27% of transactions cause 0.1% price change. With this observation, we implemented our Crystality AMM. This is unified liquidity pool, but supports the parallel execution for small transactions. And for the large transactions, we handle the large transactions sequentially. These are our preliminary results. We can obtain more than 10 times better speed up over sequential execution method in 16 parallel EVM. Last part, we implemented GPT-based auto transpilers. We let the ChatGPT learning our language specification and 6 contract example. With that, ChatGPT can transfer 22 contracts from 45 inputs. And with one more step, with a few short learning methods, developer prompts, the ChatGPT for old model can generate 10 more contracts into Crystality code. This picture showed 2 different cases, one successful, one failure. And for the failure one, we found that the ChatGPT, the auto transpiler struggled to retrieve the binary of function output in ERC 721 contracts. This is what we are working right now. Okay, this is the major thing about my talk. My talk includes the program model and our Crystality implementation and a very brief introduction about the Crystality AMM, about the application built on the Parallel EVM. Thank you for your attention. I'm happy to take any question. Yeah, it's fine.
What are you most excited about in this space? Like, what are you excited? Oh, sorry. What are you most excited about in this space? Like,
Oh, okay. Yeah, it's very. I'm very excited because this one I think is we can use our method to improve the execution speed on the Ethereum, and we provide the total EVM compatibility. That means you don't need to change anything underlying the underlying EVM system. I mean, you don't need to change EVM, you don't need to change consensus layer, you don't need to change anything under that part. Then only care about the execution layer and the application. This is the most exciting part for me. Yeah. Okay, thank you.